We know from quantum mechanics that when you have a molecule electron, you excite the electron to upper state, and when it relaxes back to the ground state, it emits a photon, which we call fluorescence. And you can do this with two photons. So if two photons meet at the same time at the electron, at the molecule, with half the energy of the required gap, then they excite the molecule, and then it relaxes back to the ground state and emits a photon. We call it fluorescence. We detect it, and that's it. So these are the two photons that really have to meet at the same time, at the same spot, at the molecule that you want to excite. You can also do it with three photons, so you don't have two-photon microscopes. There are three-photon microscopes, even four-photon microscopes, so there's a little bit of variety in this one. And how do you do that, right? So this is the problem, how to excite a molecule with two photons at the same time, at the very same time. So you take a femtosecond laser, which nowadays femtosecond lasers are an ubiquitous tool in modern production and micromachining and also quantum optics and all that stuff. So you take a femtosecond laser, which is basically emits flashes of light, very short. And they are very short, right? They are probably they are as short as a hair is thin. When you could imagine they, zip across your face, and you could see it actually. You would be able to see it. It's very thin. These flashes of light. So these flashes of light, they come to the tissue, and they are focused with the objective to a tiny spot. So you can imagine this very thin sheet of light, flash of light, travels through the objective, and it's focused into the tissue. So at the focus spot, what remains is a really small dot point of high intensity light, and otherwise it's dark. On top of that and below that it's dark. So this tiny spot then interacts with the tissue, and those two photons or multiple photons interact with the tissue, and then the molecule is excited and falls back to the ground state, and emits a fluorescence photon, and then you can detect it. So that's the principle of the two-photon microscopes. And so we know that photons of half the energy, they have a longer wavelength, which means, because as we said before, brain is highly dense and packed together, so light is scattered when it travels through the brain, and you have longer wavelengths. So they penetrate deeper into the brain, and when you go from a two-photon to a three-photon microscope, where you even use longer wavelengths, they're even less scattered, so they can penetrate deeper into the tissue. So two-photon microscope typically goes to maybe 500, 600, 700 microns, and a three-photon goes to 1 millimeter, sometimes 1.5 millimeters. So it really depends also on the sample, but that's how you can penetrate into the tissue. Compared to a conventional confocal microscope, where probably some users know about it, it gives maybe a factor of between 5 or 10 in penetration depth compared to a confocal microscope. And there's another advantage: you can do better time-lapse imaging. So because it's more gentle, a two-photon microscope, because it only interacts in this very tiny spot with the tissue, it's much more gentle on the tissue. So photo bleaching or phototoxicity is less an issue. That means you can of course work with a sample over a much longer time scale. So doing time-lapse imaging, or just see how the cells grow or split or behave over time, which is better to do with a two-photon microscope than with a conventional microscope. And as I mentioned before, the label-free imaging comes into play. So SHC, THC, but also coherent Raman imaging, these technologies, they can be implemented with a two-photon instrument, giving you additional access to optical techniques that you don't have with the conventional confocal microscope. But still, the confocal microscope is still around, and I think there's still a big market for it, because it's not that complicated. People are used, you have a CW laser, people are used how to use it. It's cheaper usually than a two-photon microscope. So the confocal microscopes, they are definitely still there, and they have their place in the market. But eventually, I mean, our opinion is that a two-photon microscope is fundamentally much more powerful than a conventional confocal microscope.